This is where the fun really begins. This is the point of chapter 1, okay? And we've already hinted at a little bit of this. We've already done a little bit of this 1.6 stuff, modeling real life situations, real life applications with linear functions. Now, again, one of the things that we'll have to think about is we're doing very simple models. We're just doing linear functions. If we got better models of more important things, the math would get way harder. Okay, so we are just kind of starting with some simpler models, but they are still useful models, and we'll see a few of those in this section. This can be a little tough because there's not always an obvious thing that you're going to do. What we're going to start with is just a basic general problem solving strategy that can work for any application problem for linear functions. Okay, so we've got this list of 8 things that you can go through to solve a problem. I'm not going to go through them now, but what we're going to do is we're going to look at the first example problem and then use each one of those steps and see how those steps can kind of work with us. And I probably won't use the steps on every problem, but they're a good thing to go back to if you're stuck. Okay, so if you're ever feeling lost on one of these application problems, these problems with a bunch of words, go back to those step-by-step things and see what's going on. So let's look at this situation. We've got a company and they purchased $120,000 worth of new office equipment. They expect the value of that office equipment to depreciate by $16,000 every year. Um, normally depreciation is like exponential, but we'll model it with a linear function here. So we're supposed to find a linear model for the value of that office equipment and then find and interpret the horizontal intercept and determine a reasonable domain and range for this function. So there's a lot going on here. Let's say this is part A, find a linear model. Part B will be find and interpret the horizontal intercept. And then part C will be to determine a reasonable domain and range for this function. The book likes to do this a lot. They tell you to do 50 things in one line, and I usually split them up into different ones, but I didn't split it up in this one. Let's go through the problem solving strategy. We're going to start with number 1, identify changing variables and define those variables and maybe sketch a picture. So what variables do we have? Number 1, what variables do we have? Let's see. Well, we're purchasing office equipment. The value's depreciating. We want a linear model for the value. Oh, okay. So the value seems like something that we care about, right? We're curious about the value of this equipment. Let's write a variable for that. Let's say the value V in dollars. So as soon as we have identified one of these quantities that we're interested in, we say, well, how is V changing? V, the value, is something that we care about. Well, how is it changing? It's changing every year. And as soon as we know how it's changing, that tells us another quantity that we care about. It's changing every year, so we should really be thinking about how many years are going by. So we could say years Y that have passed since purchase. So now we're thinking about, okay, what's the relationship between these two variables? What's the relationship between the value and the years that have gone past? And we already have some information in this paragraph. So we've got the changing quantities. It was the years and the values. And we included the units and gave variables for them. Okay, years, dollars, V, Y. Sketch a picture or define a coordinate system. I don't think a picture or a graph is really going to help just yet. A graph actually could kind of be useful though, right? Yeah, we could draw a little graph, right? We know that at the start, if you wanted to, right? At the start, at year 0, the value is 120K. We're probably jumping ahead a little bit. And we know that every year, right? Every year this value is decreasing. So after 1 year, After 1 year, oh my program is freezing. After 1 year, that will have gone down by 16,000. So now we'd be at 104,000 after 1 year. And then another year, it's going to go down by another 16,000. This is going to be 104,000. Well, I really shouldn't use commas here, right? We're using commas for ordered pairs. So it'd be kind of weird to use commas for multiple things. And then we could draw another point and so on. And we can see a picture of what's going on here. That's not really step 1 anymore. I'm kind of jumping ahead. But there's no one way of doing these problems. You can do these problems in any order. You don't have to follow this step-by-step method. In fact, I don't like step-by-step methods, but I'm including them so that you can have an example for if you get stuck. Let's go on to number 2. Carefully read the problem to identify important information. Look for information giving values for the variables or values for part of the functional model. Okay, look for values for the variables or things like slope or initial value. Okay, well, we already got some stuff here, right? This is at the start, right? This is the value at start. Starting value. This is going to be our B value for a line. And we know how it's changing. It's changing by 16,000 every year. We know that's going to be how it's changing. This is the change. This is our slope. Good. Okay. We can reread through the whole problem again. See if there's anything else we missed. But really only the first 2 sentences up to here are the information. Everything else is just telling us what we need to do. Step 3. Again, that was step 2, if you will. Step 3, carefully read it wants you to read the problem 3 times, okay? And that's a good rule of thumb. Make sure to read and reread so you know everything. Read the problem again, identify what we're trying to find, identify maybe what we're trying to solve, what we're trying to interpret. So we're doing part A. We just want a linear model for a value. What does linear model mean? What does linear model even mean? It means a linear function that, bless me, sorry. It means a linear function that describes the situation. Okay. That's what linear model means. When we talk about models in general for math, it's how can we describe a situation? And we aren't going to describe it perfectly usually. Just like in a lot of biological models or a lot of physics models or a lot of chemistry models, we just kind of our best approximation. That's what linear model is going to represent. And that's what we want. So we want an equation, a linear equation. So I'm going to start by writing y equals b plus mx. But I'm going to rewrite this. This is what a linear equation normally looks like. But what's our output? It's not y anymore, right? Y is the years that have passed. Y is actually our input here. Our output is the value. The output's what we care about usually. So our output is v, is b plus m times our input, and our input is the number of years. So this is a line in general. And this is our line that we care about. This is what we want to find. And in step 2, we already found what b has to be. We already found what m has to be. So we're well on our way to solving this problem. Number 4 says, find a solution pathway. That just means, how can we figure this out? Using the provided information to get to what we're trying to find. Okay, so this is what we're trying to find. How can we get there? Well, we have a b, we have an m. Our solution pathway is just plug in b and m. That's how we can go from what we know in number 2 to what we need in number 3. Number 5, when needed, find a formula for the function. We already took care of that. Y equals b plus mx. Solve using what we've done. Okay, so let's do it. Let's use our pathway. So V is going to be B, and we said B was 120,000 plus M. We said M was decreasing by 16,000. Ooh. So M is going to be negative 16,000. Watch out for that. If your rate of change is decreasing, that means your rate of change is negative. So it's not going to be plus 16,000 anymore. It's going to be minus 16,000 times our input variable, which is y. Good. It wanted a linear model. We found our linear model. There it is. That will be our linear model. And again, sometimes you can write it in this notation just as variables. If you wrote it as function notation, you could say v is a function of y. And you could write it like this. Anyway, step 7. Does our answer seem reasonable? Does it make mathematical sense? Okay, well, I don't know. Does it? Let's see. If we plug in some points, right? If y equals 0, what is our value going to be? Well, it's going to be 120,000 minus 0. Okay, that one makes sense. Initially, the value is 120,000. If y equals 1, well, we get 120,000. V is going to be $104,000. Okay, that makes sense too. A year later, it went down by 16,000. Okay, it's making mathematical sense. If we forgot to make our slope negative, if this was our slope, a positive, then in step 7 is where we would catch that. And that's why that step 7 is so important. Okay? Once you come up with an equation, play around with it a little bit, especially in these longer problems, to make sure it's actually working the way that you think it should work. I do this all the time. Okay? And I've done a lot of math. But what it's actually, I'm not lying to you. It's literally my first thing. When I'm trying to come up with an equation for anything, whether it's for class, whether it's for my own life, because I do use math a lot in my own life, and in very nerdy ways, the first thing I do when I come up with an equation is I plug in some values and see whether this equation really makes sense. So that's a really good one. I like this one. I'm going to give 7 a star, a smiley face, and say important. Number 8, clearly convey your result using appropriate units and answer in full sentences when appropriate. So we can do that by saying, just reminding everybody, like I boxed the answer here, but I said what V and Y were up here. But if you're really being very, very good, you could say this is the relationship where V is value in dollars after Y years. And that's like a really good answer. It puts everything that the reader needs to know in one spot, instead of making them look around for what V and Y actually talk about. All right. So there we go. That's part A. Let's do parts B and C of this problem. We're mostly done. Find and interpret the horizontal intercept. Remember, horizontal intercept, that's where it crosses the horizontal axis. That's where it crosses down here. Oh, we have a line though, so it's going to cross like, our line's going to go like way over here. It's going to be when the output is equal to 0. When the output, and our output here is V, is 0. We need to find it and we need to interpret it. So we have our equation, right? We found our equation right here. Let's just find out what happens when V is 0. So if V equals 0, we replace the V with a 0. 120,000 minus 16,000y. Solve this equation. We can add 16,000y to both sides. That's going to tell us that 16,000y is 120,000. So if we want to know what y equals, we just divide both sides by 16,000. We're going to get that y is equal to, I have no idea, 120,000 divided by 16,000. That's not right. There we go, 7.5. What does this mean? When the value is 0, the year is 7.5. 7.5 years have passed, right? That's what y refers to. So that doesn't make a lot of sense. So let's switch the order of that sentence. Instead of saying when the value is 0, 7.5 years have gone past, flip the direction of the sentence and say, when 7.5 years have gone past, the value of our office equipment is 0. Okay? Or another way of saying it a little bit more naturally is, after 7.5 years, our equipment is worth nothing. Oof. Again, according to this model. This model does not perfectly describe reality. But according to the model, that's what we've got. What about part C? Determine a reasonable domain and range for this function. Okay. Domain, range, we'll write our answers in interval notation. Domain is going to be the inputs that make sense. And graphically, we can look at it like this. Right? We know that this is the point, 7.5, comma 0. Well, that's our domains right there. We bought it at year 0. Anything less before year 0 doesn't make sense. It didn't have that value to us before year 0. So year 0 is the first year that makes sense. And I would say that after 7.5 years, things don't make sense after this point either. Because they're never going to have a negative value. Not really. Unless you think they're worth nothing and it's going to cost stuff to get rid of them. But this model won't make sense anymore after 7.5 years. A lot of times in applications, the domain has a lot to do with when are things positive. Not always, but often has to do with when are things positive. If we were looking at our input being a discount, it wouldn't just have to be positive though, because a discount of 150%, for example, wouldn't make sense. So it's not always the case, but that's usually a good place to start with for domains. Make sure that these physical quantities are positive. The 0, make sure that the input's positive, and the 7.5, make sure the output, the value, is positive. What are the y values going to look like on that range? This is where the graph really did help. The y values, well, the smallest value that makes sense is 0, and the biggest value that makes sense is 120,000. That's a domain and range that makes sense. The range usually is dependent on the domain, because the range is output values, and output values are dependent on input values. So that's just one problem. These problems are long, they're more complicated. That's why we have this step-by-step approach to help you through them. We do a lot more examples in this section. Most of this section just is examples, giving you extra practice, letting you see different types of problems. Okay, so let me know if you have questions as you're going through them. Don't worry if you're feeling overwhelmed. You can reach out and hopefully I can help with that. Anyway, I think that's just about everything I wanted to say here. Have a good day.